Hi everyone, we'll be solving the questions about limits today, and this is the third worksheet. If you have any question, you can attend office hours, which is on Fridays between 5 and 7 p.m. So let's start. The first one, for the first question, we are given the graph of some function f. Here we have. We'll evaluate these ones. So for the first part, for the part A, here we have x, which is approaching to from left-hand side, okay? Here we have x, okay? This is the line for x, this is the line for f of x, or we can say y. So we're approaching 2 from the left-hand side, and we see on the graph, it's approaching to 3. So it is 3. What about this? Now we're approaching from right, okay? And on the graph, we see it's approaching, the values of f are approaching to 1. Here we have, so it's 1. What about part C? It does not exist. Why? Because these two limits are not equal. If this existed, then they should be, or they would be, equal to each other, as by definition of limit. As they are not equal, then this limit does not exist. Okay, so what about this f of t2? It is, here we have the empty dot, and here we have the dot, right? So it's defined on 2, which is by 3, okay? It's 3. What about this? Now, to say the limit, to evaluate, to compute this limit, we need to compute the left and right hand side limits of f. Okay, what's this? So we're approaching 4 from left, and see on the graph it's approaching to 4. So the limit is 4. What about the right hand side? On the graph, we see it's again 4. So they are equal, then this limit exists and it's 4. Okay. What about this? F of 4. It is not defined because here we have the empty dot. So we say it is not defined. Okay. For limit, we say it does not exist. And for these values, we say it's not defined. Here we have this function, okay, which is defined piecewise, okay. So first we sketch that. Remember, we start with the function that we know better. We know sinus, right? So we know that sinus is 0 on 0, and it's, let me write first these values. It's 3 pi over 2, sorry. Okay, so on 0, at the point 0, sinus is 0. What about sinus minus pi over 2? It is, here we have minus 1 and 1. So it is minus 1. Okay. And for minus pi, it is 0 again. Okay. So its graph is like this. Okay, it's like this. This is the graph of sinus x when x is less than 0. Okay, what about this 1 plus sinus x? We just shift the graph of the function upward as we here at 1. So we obtain this graph. What about this? You should already know these ones graph, so I don't explain it again. So we need to find this value a, for which the limit of f when x is approaching a does not exist. So here we have this graph. So remember, here we have x is less than 0, so it is empty dot, okay? But here we have the equality, and when x is 0, cosine 0 is 1, so we have this, okay? Okay. Now we see on this, we need to only check these values, okay? So here we have the value of f, the limit of f when x is approaching 0. Okay, it's this, which is 1. Okay, so it exists. It exists when x is approaching 0. Okay, what about this, for example? We're approaching from left and right, and we obtain the same value. What about pi? We checked 0. We said it existed. And what about pi? Here we have. So we are approaching from left, okay, and we see it's -1. And from right, it's 0, even if it's not defined, the limit is 0. So they are not equal because here we obtain 0 and there we obtain -1. So the limit of f when x is approaching pi does not exist. So the value a is here pi. Okay, now we evaluate the limit of the given function. Here we have. So what do? We first multiply this one by x and this one by 4. Here we have x plus 4 over 4x. And we had already the denominator 4 plus x. Now we have x plus 4 over 4x times 1 over 4 plus x. We can simplify. So we can simplify these ones and we obtain 1 over 4x. We just put here x equals to this minus 4 and we obtain minus 1 over 60. Okay, now we have this function. What do? When we see some function which includes these square roots, we just multiply it by its conjugate. By conjugate, I mean if we have here minus, then we multiply it by the plus one, okay, but by the one with plus. So here we multiply it by this, okay, it's conjugation. So, but we need to divide it by that 2 because we need to obtain the same thing, okay? We cannot change anything here. So we both multiply and divide it by this conjugate, okay? So here we have this numerator, and in the denominator we get the same, of course. So if you do some operations here, you get 2x over this, and we simplify this x and this x and get this 2 over square root of 1 plus x plus square root of 1 minus x. Okay, here we just put x equals to 0 because we don't have any function which is not defined on 0, so we can put x equals to 0 and get 2 over 2, which is 1. So we have some attention here because this is important. If you don't know if the limits separately, the limits exist, then you cannot separate this given limit. Okay, if you don't know that and that separately exist, then you cannot separate the given limit. Okay, so as we don't know if their limits exist, we just make some operations for that, for the given limit, okay, given function. So let's compute for the left and the right ones. So what about this? Here we have 1 over x. When x is approaching 0 from left, as we have here minus, then this is minus infinity, okay? Because here we have something less than 0, okay? Okay, so we have minus infinity. What about that? As x equals to 0, we can consider that x equals to 0. X is almost equal to 0, so we can consider x squared equals to 0. So we get here 1 minus infinity minus 1, which gives minus infinity. So from left, we have this limit. What about this from right? So here, as you can guess, 1 over x gives us plus infinity. And here we have the same conclusion, 1. So we get plus infinity. They are not equal, they are not even some number, some real number, so the limit does not exist. Here we have this function. So our variable is h is here, okay? So we see x as constant. What do? We multiply this one by x squared and this one by x plus h squared. So we get this numerator, and in the denominator we have the same h. So what about this? We just write this parenthesis clearly and get these values, okay? And in the denominator we have x plus h squared x squared times, here we had h, so we have this denominator, okay? So if you do some operations here, you get this value in the numerator, and in the denominator we have the same, the previous one. So what happens here? Here we had minus 2x minus h over this. We simplified here h, okay, and get this. So we try if we can put h equals to 0. Let's try it. So if we put h equals to 0, here we get minus 2x, and in the denominator we have x to the 4. As we see x as a constant, here we can imagine like we have some constant number, okay? So we have minus 2 over x to 3. We simplify x's here and get this value, okay? For this question, we'll use the squeeze theorem, okay? Let's remind that. So here the statement of the theorem. It says if you have 3 functions with this inequality, and if you know that these boundaries, right, f and h are like boundaries for g, if their limits are the same, they exist and the same, then you can say the limit of this one, the middle one, is L, okay? So here we're given this function. We want to find its limits when x is approaching 0. So we need to have, if we want to apply this theorem, we need to have the statement, right? We need to have this inequality, we need to have these limits, okay? So here we have this function, okay? I set that function to be equal to f of x, okay? But they are not the same. Here we have g, okay? It would be better if I said g, but sorry. So we have this function. I want it to be in an equality like this, okay? So remember that sinus, the function sinus, is in between -1 and 1 for any real number, for any angle here. It's in between -1 and 1. So for pi over x, we have again the same inequality, okay? Because pi over x is in real numbers again, so we have the same inequality. So, but we need to obtain this function. To obtain this, okay, we need to multiply this inequality by this square root. So we multiply it by this square root of x to the 3 plus x squared and get this one. Now we check the limits of that and that. Here we see when we put x equals to 0, we get 0. So their limits are 0. They are equal though. So we have this condition and this condition. Okay. So our function is in the middle of the inequality, as in here, and the boundaries limits are equal. So what do we obtain? We can conclude like this, right? We can apply the theorem now as we have the assumptions. So the limit of our function is again 0. As we here obtained 0, its limit should be 0 too. Okay. Again, we'll find the limits. Okay. So we'll check from left and right first. Here we have the function 2x minus 1 over the absolute value of 2x to the 3 minus x squared. So what happens when we are approaching 1 over 2 from the right hand side? We first write it clearly, okay? Here we have, in the parenthesis of x squared, we have 2x minus 1, right? In the absolute value. Okay, so we can write it separately here. Okay, and we know x squared is always positive or equal to 0 because it's real. Okay, so we can write it outside of the absolute value. What happens here? We have 2x minus 1. Okay, when we are approaching 1 over 2 from the from the right, it will be greater than 1 over 2. Okay, so when x is it's a little bit greater than 1 over 2, but still it's greater. So when we put something which is found the right of this value, this will give us something positive. So it is the same outside of the absolute value. It remains the same. So here we simplify these ones and get 1 over x squared. When we put x equals to 1 over 2, we get 4. And here we have the same, right? We have the same function. So we again write it separately. So here x is approaching 1 over 2 from the left-hand side. So this will be negative. Thus, we need to write it by multiplying by -1. So we have here 1 minus 2x. As it's in absolute value, we need to multiply it by -1 to write it outside of the absolute value. So we simplify these ones and get -1. Here we have minus 1 over x squared. Now we put x equals to 1 over 2 again and get this, minus 4. Here we had 4, now we have minus 4, they are not equal, so the limit does not exist. Actually, we do the same things. Here we have the absolute value of x. When we are approaching 0 from the right-hand side, we have something positive here, right? So we can write it outside of the absolute value exactly itself. So we have 1 over x minus 1 over x, okay? We get 0 there. When we're approaching from the left, we have here minus x. This will be equal to minus x as it's negative here. So we have 1 over x minus 1 over x. It will give us plus 1 over x. So we get 2 over x. When we put x equals to 0, we get 2 over 0, which is minus infinity, which gives minus infinity. So the limit does not exist. We have this function, which is again defined piecewise. So here we have these 3 parts of the question. First one, we need to compute the limit of f by approaching 1 from left and right. So let's first compute this one. We are approaching 1 from the left. So here the values of x are less than 1. So on this interval, when the values of x are less than 1, the function is defined by this, right? X squared plus 1. So instead of f of x, we can write x squared plus 1. Now, what do we have? We put x equals to 1 and get 2. For this one, we have the values of x which are greater than 1, right? Because we're approaching 1 from the right. That's why the values of x here greater than 1. So f is defined by, on that interval, x is defined by this equation. So we get this, and we put x equals to 1 and get 1. So here we had 2, here we have 1, they are not equal, so the limit does not exist when x is approaching 1. Okay, for B we find that. Now we'll sketch the graph. So first, let's find the definition of f, or the value of f, when x equals to 1. Here we have the equality. Now we put x equals to 1 and get minus 1 squared, which is 1. Okay, here we have this dot. So what's happening here? We know the graph of x squared, right? This is x squared. This is x squared. We have x squared plus 1, so we shifted, as in here, we shifted 1 unit upwards. As it's defined until x equals to 1, we sketch it until 1, okay? So here we had x equals to 1 and we get 1. And what happens here? We have x minus 2 squared. We had x squared here. Here we have minus 2. So we shifted 2 units, okay, to the right. Okay, as in here we have 2. We shifted 2 units to the right. So we have this graph of the given function. Again, we'll find the limits. So for this limit, we can write the denominator like this, in this form. We just write this one, x to the 3 minus x. We write it in the parenthesis of x. Okay, here we have. we had +1 here. We write the same. So now we write this denominator in the parentheses of x squared minus 1 as in here. So we have x plus, this will be 1 over x squared minus 1, okay? Because if you multiply it by x squared minus 1, here you have x squared minus 1 times x, and if you multiply this one and this one, you'll get 1, the same. So we have exactly the same limit, okay, the same function in here and here. So if we simplify this and this, we get -1, and this remains the same. So here we have. Now what happens when x is approaching infinity? Here we have 1 over infinity, which is 0, which is approaching 0. And x is approaching infinity, so here we have, for this part, it's approaching infinity. -1 over infinity, it's 0. For this, we have this function now. We just rewrite this, okay, as in this form. It's the same because x times square root of x equals to x times, this can be written like this. Here we have times x to the 1 over 2, and this can be written like this, which is x to the 3 over 2. Okay, this is 3, this is 3 over 2. So we have the same. Now we rewrite it as in this form to have something similar like this. Okay, now what do? We just here we have in the parentheses of x square root of x minus x, we have this 2 for the first two entries, okay? Oh, sorry. For that one, we rewrite here. And for 3x, we separate it for 5 as 5x and minus 2x, okay? Here we have 3x and minus 5. We have the same. So in the parentheses of this, we rewrite this denominator, and 2 plus, we have this 2 plus this fraction. So what do we do here? We need to multiply it, but first we simplify these ones and get -1 here. Now what do? We multiply it by the square root of x plus 1, okay? And we have this, okay? So we simplify this and this now and get this, okay? So we rewrite this parenthesis and x, we rewrite it, okay? It's exactly the same. They are exactly the same. So, and finally we rewrite this one, okay, which is this, right? If you multiply this one by the square root of x, you get the same with this. So we have this. Now what do? When x is approaching infinity, this will be approaching 0, and again 0, this will be approaching to 0 too. So here we have 0, though we get -1 over 2, okay? As x is approaching infinity, we want to obtain something like this, a over x, okay, some function in terms of x here in the denominator, and some constant number here, because we know when x is approaching infinity, here we'll have 0, it will be approaching 0, okay? So our work will be easier than the previous one, okay? That's why we do the operations. Now we'll again find the limits, but recall this theorem. So it says if you have some function in this form, and if x is approaching 0, then this limit will be equal to 1. Here in the part A, we have this function, sinus 3x sinus 5x over x squared, and x is approaching 0, as you see. So what do? We have this sinus 3x over x, sinus 5x over x. We had the same, right? We had x squared. We separated it, okay? So, but remark that in the sinus, in the function of sinus, we have x, and in the denominator, we have again x. So the inside function of sinus and in the denominator, we need to have the same function. So that's why we multiply this denominator by 3, but we need to have the same thing with this one. That's why we multiply it by 3 too. Okay, for that one, we do the same operation with 5. Okay, so we can now separate the limits because we know they both exist by the theorem. Okay, we can separate it with these two limits. Okay, we write this 3 outside of the limit, and for 5 we do the same thing. So outside of the limits we have 15. Now by the theorem, this will be equal to 1 and this is equal to 1 again. So we have 15. For this one, we have this limit now. We have sinus x minus 1 over x minus 1 times x plus 1. Remember, we need to have same things inside of the function sinus and in the denominator to apply this theorem. So for that one, we first separate or rewrite the denominator of the given function. Then we change the variable. Here we write u equals to x minus 1. Then if we add 3, both sides of the equality, we have u plus 3 equals to x plus 2. So we have, why did we compute that? Because inside of the function in the denominator, we have x plus 2. That's why we wrote that. Now what do we have? We have sinus x minus 1 over x minus 1 x. We had that, x minus 1 times x plus 2, which is equal to this one. I made a mistake there, I guess. Yeah, I rewrite that. Sorry, this is unnecessary. Okay, we had that. So instead of x minus 1, we write u. Okay, and here we have x minus 1 again. That's why we write u here too. And x plus 2, we computed there. It's u plus 3. Why we write this? When x is, remember, when x is approaching 1, here we have x is approaching 1, then this will be approaching, this will be x minus 1 will be approaching 0. So u will be approaching 0. That's why we write it there. So we have sinus u over u times, we separate the limits because we know they both exist. This we know by theorem, it exists. And this, it's obvious if we put u equals to 0. So we separated them. Now we have by the theorem 1 for this part. And for this one we just put u equals to 0 and get 1 over 3. So finally we get the conclusion. We get the answer. So this is the last question. Here we have x squared over square root of x to the 4 plus 1, okay? So now first we write the denominator in the parentheses of x to the 4 and get this one, okay? We can write it outside of the square root as in this form, the absolute value of x squared. We know x squared is always positive, so we can write it outside of the absolute value. So we have this. Okay, I made a mistake there. This is 4. Okay. Again, this is 4. So when x is approaching infinity, this will be 1 over x to the 4 will be 0. So this will be 1. Okay. Sorry. So we simplified that and that for this part. When x is approaching infinity, this will be approaching 0. This will be approaching 1 then. And we have 1 over 1, which gives 1. Okay. Now we are given this limit. To find that, we multiply it by its conjugate, as I said before. Okay, we multiply with the plus 1. So here we have this limit. Now we multiply the denominators, the functions in the denominator, in the numerator, sorry. So we have this. Now we have in the numerator x, okay, we have the same denominator with the previous one. So we write that in the parenthesis of 9x squared and get this. So we can write this 9x squared outside of the square root as in this form. Now we see x is approaching infinity, so it's positive, so we write it in this form. Now we write this denominator in the parenthesis of 3x and get this one. When x is approaching infinity, we just simplify x's here. When x is approaching infinity, this will be 0, this will be 1, and 1 plus 1 will get 2. So 1 over 3 times 2 gives us 1 over 6. Okay, so this was the last question. If you have any other question or any question with these ones, any problem with these ones, you can attend the office hours. Okay, so see you.